All right, so part 2 of our chapter 6 lecture is going to involve quantum mechanics and kind of introducing how the shapes of different orbitals around atomic nuclei have come about. And when we say atomic orbitals, what we mean is the area around an atom's nucleus where an electron of a certain kind will be found. And in order to understand this, I want to introduce you to this idea of a dot density diagram. So over here on the right, we have a dot density that talks about the probability. Basically, this is a probability map of finding an electron in a certain area. Think of the nucleus of an atom at the very origin of the three-dimensional axes, and the different blue dots all indicate the probability or a single probability of finding an electron in that specific area. And what you can see is there's this kind of like three-dimensional spherical shape that kind of centers around this axis. It has a definite shape, but it definitely fades as you go. So there's a really high probability in that center area, and then the further out you get, the less and less likely you are to actually find the electron. So this idea of being able to create probability diagrams of where you're going to find electrons around atomic nuclei is called quantum mechanics. Quantum mechanics also takes into account how to use wave mechanics and wave equations. We are not going to do this in this class. This is more of a third year of chemistry in your graduate program kind of thing. It's called physical chemistry. What we just want to know is that this wave equation is denoted by this letter psi, and that all it does is give us this kind of a diagram. And what it's going to predict for us is whether or not we will find an electron, and if we find that electron, in what shape around the atomic nucleus will that electron be found. Now, that being said, we're going to talk about quantum numbers in this chapter. And these quantum numbers can be kind of confusing to students because what they are is a way of describing electrons. So think about how there are so many ways you can describe an object. You can talk about shape, you can talk about color, you can talk about size, you can talk about behaviors, you can do all kinds of different stuff. And quantum numbers are our way of describing specific electrons. Now, orbitals themselves are going to be described by a set of 3. Then electrons get described by a 4th. So orbitals and their shapes are going to be described by 3 different quantum numbers. And this idea or this term of quantum number is a misnomer. It's very misleading. A quantum number is really going to be denoted by this letter N. The principal quantum number, which is the most important of them all because it tells us at what energy level we're at, are going to be numbers that range from 1 up. And they're going to be whole numbers of 1 or greater. Quantum numbers, quantum number n indicates the size of our orbitals as well. So if we start at 1, it's going to be small. And if we go up to like 3, 4, 5, the n of 5 has an even larger version of that specific orbital. The second quantum number is going to be L, and L defines the shapes of our orbitals. So any value of L can be any number from 0 ranging up to a top value of n minus 1. So for instance, if n is 2, your values of L are all whole number integers ranging from 0 up to n minus 1, in this case 2 minus 1, so 1. So the values of L for an n of 2 would be 0 and 1. Now, in order to understand what that means, there are different orbital shapes that go with different values of L. So if you have an L of 0, the type of orbital is an s orbital, and we'll show you some pictures here in a little bit, but the shape of the orbital is going to be s. The shape of an orbital with an L of 1 is going to be p, the shape of a d is going to be, L is going to be 2 is going to be the shape as a d, and L of 3 is going to be a shape with f. And we'll look at pictures of those here in a second. For now, we're just kind of introducing the quantum numbers. Later on, we'll practice with how to actually assign quantum numbers, and that's going to be the next video for you to watch. The magnetic quantum number is just going to be one that describes the three-dimensional orientation. And we'll see an example of the different types of orbitals. But what that means is in order to figure out the values of m sub L, the integers all can range from negative L, this is an L, to positive L, and that includes 0. So for instance, in our previous example, we had an L of 1. So we know that the shape of the orbital is a p, but if L is 1, all numbers, whole numbers including 0, between negative L and positive L are -1, 0, and +1. And that being said, that means there's 3, because for every value of m sub L, you count them, and that's how many orbitals there are. So let's say we had an L of 2. It would be -2, -1, 0, +1, and +2. So there are 5 values of m sub L, which means 5 possible d orbitals, and so on and so forth. And so what happens is we are going to put all of this together. And like I said, please don't freak out. What we're going to look at is how orbitals with the same value of n all form shells, and then everything within a shell are called subshells. So for instance, if we start over on the far left of this table, we're looking at values of n that have 1. The possible values of L are 0. Remember, the rule for L is that all values between 0 and n minus 1, if n is 1, 1 minus 1 is 0. So the only possible value of L is going to be 0. The subshell is then going to be designated 1s. Because the value of L is 0, the only designation it can have is s, and the n comes in front. Possible values of m sub L, remember, go from negative L to positive L. In this case, since L is 0, there's only 1, which means there's only one s orbital. And that means a total number of s orbitals is going to be 1. Again, we're going to go through and we're going to talk about what these numbers actually indicate and what they mean in more detail in the next video. For now, what I want you to see is that when it comes to values of, say, s orbitals, remember an L has to be 0 for there to be s orbitals. They're named s, I'm thinking, because they're spherical in shape, right? So that probability diagram we first saw translates to an s orbital of a certain size. And this is actually a 1s orbital with a 1s orbital. Now, as the number in front gets larger, so this is the n value of 2 and 3, as that number gets larger, you can see that the sphere gets larger, which means the distance from the nucleus gets larger and larger. So these spherical objects, you're going to see s orbitals and p orbitals and d orbitals. Those shapes are really just identifiable probability diagrams. So what that means is, instead of drawing this every time, which is super confusing and doesn't have defined margins, we're going to simplify it to something like this. So the 1s orbital has a certain shape and is a certain size, and it defines where we can find an electron around the nucleus in that particular energy level. A 2s orbital has double the size in this particular diagram, and it defines, again, where you can find an electron around that nucleus, and a 3s orbital even larger. So you can see as we go from one energy level to the third energy level that the area around which we might find that single electron gets larger and larger and larger. What we want to actually zoom in and see here, okay, so this is kind of important, is that we have several different areas within each of these different probability diagrams where you are more and less likely to find the electron. We refer to the different areas along our, so let's look at like 3s over here. You see this little like white area and this white area. Those are referred to as nodes. Those nodes are areas where you have no probability of finding the electron. And that only happens as we get beyond the 1s designation. So for something with 2s, the number of nodes is always going to be n minus 1. So for instance, the 2 in front is the n of the 2s orbital. N minus 1 is 2 minus 1, so there's one node. Okay. Over here we have 3 in front of the s, which means n equals 3. So there are n minus 1 nodes, which is 2, so there are 2 nodes along this particular orbital. P orbitals look a little different. They look like barbells, if you will, or like smushed balloons, whatever you like. The L for p orbitals is going to be 1. Now remember, L is n minus 1. The L for p is always 1, and what that means is that you're going to have lobes between different nodes. So, for instance, in our spherical diagram, the node was kind of within the sphere. In a p orbital, the node is actually whatever plane the a barbell is on either side of. So for instance, the xy plane for this one is the one that that's where a node is. Now, these are just the exact same idea as the s orbitals. You see these little diagrams, and these just represent three-dimensional space where an electron can be found around the nucleus. Again, we're assuming the nucleus is still in the very center of the three-dimensional axes. For P, we said that there were three possible designations. That's what the m sub L value, the angular momentum quantum number, said. That angular momentum quantum number says that there are negative L up to positive L values for P. And since P has an L of 1, that means negative 1, 0, and positive 1. So that's a total of 3 values for m sub L, which means 3 different specific orientations. And you can see 1, 2, 3 orientations for the p orbital. D orbitals get a little more complicated since the L for a d orbital is 2. You go negative L up to positive L, that leaves you negative 2, negative 1, 0, positive 1, and positive 2, which is 5 orbitals. 4 of those 5 have this really fancy looking like double barbell shape, flower if you will, and one of them looks like a barbell with a donut. 100%, this is what they look like. A little bit weird, but remember these are just 3-dimensional probability maps of where electrons can be found around the nucleus. Again, assume the nucleus is at the very center, okay? From there, we can talk about how to do some electron configuration diagrams. And you've seen electron configurations before. This is something we will review in this chapter. One of the things to note is that if you have an electron on the same energy level, so say you have 2 electrons in the p orbitals, or 2 electrons in the s orbitals, if they have the same energy, they're referred to as degenerate. This is just like a terminology thing from your book. Remember that when we go through and we put electrons into our orbital diagrams, what we're going to see is that it's actually not common for things to have the same energy. And this is the reason why when we read the periodic table's electron configurations, we start with 1s, then we go to 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p. We've done this before. This is just describing why we read them the way we read them. A lot of times what happens is these get kind of moved around. On this diagram, we just kind of put all of the 3s on one line, but in reality, they're actually all different energy levels. So s orbitals tend to be the lowest of anything, and then p, and then d, and then f. Okay? The last angular quantum number, or the last quantum number, is the spin quantum number m sub s. What was discovered early in the 20th century was that when electrons travel through a field, they spin in one of 2 ways. They either spin positive or they spin negative in a magnetic field. When that happens, we can measure the electron as either a positive spin or a negative spin. The 4th quantum number has only one of 2 values, negative or positive spin. Okay, plus 1/2 or minus 1/2 is what we designate it. What that means is the positive spin, the spin quantum number, so this, whether it's a positive moving one direction or it's a negative moving the other, this describes why we can only put 2 electrons in each of these boxes and why they have to point in opposite directions. So if you remember asking questions about that back in your honors chemistry class last year, the answer is because of spin and because of the spin quantum number. The Pauli exclusion principle is the one we're going to talk about next, which has to do with the fact that no 2 electrons in the same atom can have exactly the same energy, which is why the spin quantum number kind of comes down to it and has an up and a down arrow when it comes to our electrons because of this particular rule. So no 2 electrons that exist can have the exact same 4 quantum numbers when it comes down to it. So this is going to be how you've seen electron configurations before. So this one in particular has a 4, then a p, then a 5. And remember that the 4 tells us where it is as far as the row on the periodic table. The p tells us the type of orbital. And then the last number tells us how many electrons there are in that previous type of orbital. So 4p5 means that we are at a certain electron in a certain part of the periodic table, and there are 5 electrons in there so far, so we want to identify the atom based on that information. In orbital diagrams, just like we've talked about in the past, each specific box represents a single subshell of an orbital. In this particular case, since the orbital is an s, we have one orbital and it has one subshell. So that being said, half arrows are then used to identify electrons. Remember that the direction of the arrow, either up or down, indicates positive or negative spin at this point. Hund's rule says the lowest energy that we can possibly fill these is going to be the one with which that we will actually do. And what that means is we fill from bottom to top. So we fill from lowest energy level to highest energy level. And we will fill a box like 2s before we go up and add an electron to 2p. Hund's rule also is the reason why when we add another electron to this particular, let's look at boron. When we add our next electron, we don't fill the box, we fill the box next to it, because it would take more energy to spin pair these two electrons than it would to just fill the box one at a time, then go back and pair because there's nowhere else to go. Remember that when we talk about these electron configurations, that there is a specific way that they are organized on the periodic table, and that means there is a specific way that they are filled on the periodic table. So we start with the S, the transition metals are the D, the nonmetals on the far right are going to be the p orbitals, the f orbitals are the lanthanides and actinides. And again, we will go over all of this again in person. For now, I'm just trying to remind you of some things you've seen. If you look at your book's diagram of all the different electron configurations, you'll notice that there are some very odd anomalies, and your book points them out. Sometimes this happens when we are at almost a half-filled S or D orbital in a specific location, and so it makes more sense to half-fill the D orbital than it does to go back and try and fill the next orbital. When it comes to lanthanides and actinides, we always fill them before we move into the D. The F orbitals get filled before D orbitals in the last two rows on the periodic table. But the anomaly the first anomaly we want to talk about is going to be the electron configuration for copper. So for copper, it's 4s1, 3d5, instead of being 4s2, 3d4. And this is because half filling all 6 of those orbitals makes more sense and is less energetically expensive than trying to fill the s orbital than only half filling 4 of the d orbitals. So when you make this, if you want to write this out on your own, you'll see that 1 electron goes in each of the d orbitals, 1 goes in each of the s orbitals. Specifically, this also happens in this location because the S and D orbitals in the transition metals tend to be very close in energy. And so in order to demonstrate that, I'm going to show you real quick this diagram. What they're saying is that happens a lot when you have this and this situation, because these are actually much closer in energy than you would think any of the other orbitals are. And it's actually really well depicted in this particular diagram. These are closest in energy on this entire table. So just to understand that there are anomalies to everything. And that's it. They also occur in the F block.